In previous examples, we looked at two sample hypothesis tests with independent samples. In this example, we're going to look at dependent samples, which can also be referred to as pair samples. Now, when you have dependent samples, that means that the samples are the same, but what we're actually doing is testing the distribution of them. So what that would mean is, with the exact same sample, how would two independent people distribute the samples? So an example that we can look at is if we have two different teacher's assistants grading in the English essays. We want to know if they grade differently or similar. So we have them grade 10 papers. These would be the exact same papers. And we test how each grade is. So again, what we're looking for now is not we're not looking for the different, we have the same sample, so we're not testing the different samples with different populations, or what we're doing is testing the distribution. So each of the grades are reported as follows, and create a hypothesis test with a significance level of 0.05 or a confidence level of 95%. So let's start with creating our hypothesis. Our null hypothesis is what we would like to assume the difference between the averages, so this is the difference of the averages, is 0. So the teacher's assistants would have the same marking. So the averages over the classroom, they will technically mark the same. Our alternative hypothesis is that the differences are not 0. So that the two teacher's assistants do have separate styles of marking and will give separate grades. Now, note, this isn't a greater than or less than. We're not saying that the difference is more than. We're not saying one teacher assistant will mark higher than the other or smaller than the other. We're saying 0 and not 0. So this is going to be a two-tailed test, because if there's a difference, if this is how a normal distribution looks with our mean in the middle, we could have a difference where one teacher assistant 1 marks lower, and it could be over here, or we could have a situation where the teacher assistant 1 marks higher. It could be over here. So this is a two-tailed test. If we were just to say higher, we'd be on the right side. It would just be a one-tailed test. So that's important when we get to our t value. So to do that, we need to use our formula. T-value, degrees of freedom, the sample difference between the paired or related observations divided by the mean, the sample standard deviation divided by the sample size squared. So first thing we need to do is to determine our degree of freedom. So we'll do that on the right side here. And in this scenario, degree of freedom will be n minus 1. We have a sample of 10. So our degree of freedom is 9. Now we need to determine our sample standard deviation. So what we can do is we can determine that over here as well. So to do this, we now need to determine, so this would be the sum of our difference squared, and our sample size. So, this is the mean difference. So let's go ahead and determine our difference and our difference squared. So to do so, we'll less assistant 1 from assistant 2's amounts. Minus 5. 75 minus 80. Minus 5. And we can add up our differences. And our difference squared. So let's move on back to our formula here. The sum of our difference squared is 25 less the sum of our difference, and where we will square it, over n, n minus 1, 10 minus 1 is 9. This is 225. Divided by 10 is 22.5. So 625 minus 22.5 is 602.5 over 9 square root. $66.94. We get 8.182. So we now have our sample standard deviation. Okay, we now need to have get our mean of the difference. Sorry, so we had negative 15 and we had 10 observations. So our mean of the difference would be negative 15 divided by 10, negative 1.5. And we have our hypothesis difference here. So this would be our UD, which would be equal to 0. So now that we can complete this, negative 1.5, that's 0, divided by 8.182, divided by square root of 10. So we have negative 1.5 divided by 2.5876. We receive 0.579. So our t, with a degree of freedom of 9, is equal to negative 0.579. Now one thing to note here is that we can never have a negative t value, so we can just make that positive when we check it. So if you refer to our two tails t chart here, so we're going to use the two tails amount. We're going to go to degree of freedom 9, and we're going to be looking for 58%. So 0.58 falls somewhere just shy of 50% and 100%. So it's probably a little closer to 50. It might be around the 60% mark, right? Because there's 0.7, so 0.58 probably falls somewhere just short of this. So we can say that our t value is 50% to 100%. We know that it's somewhere probably around 60%, but for sure it's in this range. So let's put this in layman's terms. Based on our sample, we can expect assistant 2 to have, or assistant 1 to mark, to get this higher difference. So there's a difference of 15. We can expect that between 50 to 100%, around 60% of the time. So there's no real evidence to reject our null hypothesis. We can assume that both teachers' assistants mark fairly. They don't have significant differences in their marking. And that certainly we have a significance level of 5, so that would give us 0.05. So we'd have a confidence level of 95%. And so we would need to see need to see a sample like this happen less than 5%. But if this happens, between 50 and 100 or 60 or so percent, then there's no statistical evidence to reject our null. So yeah, we can make the assumption that the teacher's assistants grade similarly.